Welcome to the second session of Module 4. In this session, we are going to discuss about transceiver characteristics, transceiver states, example radio transceivers, wake-up receivers, optical communication, and ultra-wideband communication. Sensor node architecture. What are the main components we are going to use in a single node? We have controller, we have memory, sensors or actuators, communication device, and power supply. These are the main components. The controller that is going to use to process all the relevant data, and it is able to execute the arbitrary code. Memory is used to store the programs and intermediate data. Usually, different types of memory are used for programs and data. Sensors or actuators. So this is actual interface to the physical world. Here the devices that can observe or control physical parameters of the environment. This is to sense the outer world or the physical world. Next we have the communication device. So it is going to make the node capable to communicate wirelessly, as we are using wireless sensor network. And we have power supply that is required for both for transmission as well as for the reception purpose, and for the controller it is required, and to sense the power supply is required. But usually the power supply we are going to use the batteries to provide energy to do or perform the tasks. Sometimes it is also possible to use the batteries by using energy scavenging technique. That means we can use the solar energy to recharge the batteries. So these are the main components of a wireless sensor network node. In a single node, so these components, those are essential. Controller. The controller is the core of a wireless sensor node. It collects data from the sensors, processes this data, decides when and where to send it, receives data from other sensor nodes, and decides on the actuator's behavior. It has to execute various programs ranging from time critical signal processing and communication protocols to application programs. It is the central processing unit of the node. So we have four main options. First one is the microcontroller, second is DSPs, third is FPGAs, fourth is ASICs. So microcontroller is a general purpose processor. This is optimized for embedded applications and it will consume less power. Second option is DSPs. These DSPs controllers optimized for signal processing tasks, digital signal processors, and these are not suitable here. These doesn't fit in WSN generally. FPGAs can be used, but these are good for testing. ASICs can be used only when peak performance is needed, but the problem here is it doesn't give the flexibility. So generally we can use microcontrollers. So here we can see the examples. Texas Instruments MSP430, Atmel Atmega. So Texas Instruments MSP430 that can that will use 16-bit RISC core up to 4 megahertz versions with 2 to 10 kilobytes of RAM and several DACs. RT clock is there, and the price starts at $0.49 US. Atmega from Atmel. So it is a 8-bit controller. It is having larger memory than the Texas Instruments MSP430, but it is slower than the MSP430. It is a 16-bit RISC core. This is 8-bit controller. Memory is more here. So here 2 to 10 kilobytes of RAM. Communication device. The question arises here, which transmission medium we are going to use in wireless sensor networks? Whether we are going to use electromagnetic at radio frequencies or electromagnetic light or ultrasound. Generally, we are going to use the radio transceivers. Those will transmit a bit or byte stream as radio wave. So bits will be converted into radio waves while transmitting, while reception. So that radio waves that will be converted back into bit or byte stream. Transceiver is nothing but it needs to transmit as well as it needs to receive. So coming for the capabilities, while using the interface, whether we need to use the bit level interface or byte level or packet level, that question arises. And what is the supported frequency range? And can we able to transmit the data in multiple channels? And what is the data rates? And what is the range coverage? Okay, so these we should consider before using the transceivers. For an instance, the supported frequency range typically we are going to use in WSN is somewhere in 433 megahertz to 2.4 gigahertz ISM band. And we need to consider also the energy characteristics. What is the power consumption to send or receive data? And we need to also consider time and energy consumption to change between different states, and how we can perform the transmission power control, and power efficiency, which percentage of consumed power is radiated. So these are the energy characteristics that has to be considered, and the capabilities of the transceivers that has to be considered, and we are going to choose the transceivers appropriately. Coming to the radio performance, what is the modulation technique we can use? Transceivers typically support one or several on-off keying techniques. So those may be ASK we can use, or maybe we can use FSK or similar type of modulation techniques. Radio performance also depends on noise figure. Noise figure of an element is defined as the ratio of the signal to noise ratio at the input of the element to the signal to noise ratio at the element's output. Coming to the gain is the ratio of the output signal power to the input signal power, and is typically given in decibels. Amplifiers with high gain are desirable to achieve good energy efficiency. A receiver sensitivity that will specifies the minimum signal power at the receiver needed to achieve a prescribed bit per packet error rate. Better sensitivity levels extend the possible range of a system. Next is blocking performance. The blocking performance of a receiver is its achieved bit error rate in the presence of an interferer. More precisely, at what power level can an interferer send at a given offset from the carrier frequency such that target bit error rate can still be met. Out of band emissions. The inverse to adjacent channel suppression is the out of band emission of a transmitter. To limit disturbance of other systems or of the WSN itself in a multi-channel setup, the transmitter should produce as little as possible of transmission power outside of its prescribed bandwidth, and it should be centered around the carrier frequency. Carrier sensing and RSSI characteristics. In many medium access control protocols, sensing whether the wireless channel, the carrier, is busy is a critical information. The receiver has to be able to provide that information. The signal strength at which an incoming data packet has been received can provide useful information. A receiver has to provide this information in the received signal strength indicator, that is RSSI. Frequency stability. It denotes the degree of variation from nominal center frequencies when environmental conditions of oscillators like temperature or pressure change. In extreme cases, poor frequency stability can break down communication links. For example, when one node is placed in sunlight whereas its neighbor node is currently in the shade. Next is voltage range. Transceiver should operate reliably over a range of supply voltages. Otherwise, inefficient voltage stabilization circuitry is required. Coming to the transceiver states, so we have 4 states: transmit, receive, idle, and sleep. In the transmit state, the transmit part of the transceiver is active and the antenna radiates energy. In the receive state, the receive part is active. Idle state, it is the state ready to receive but not doing so. Some functions in hardware can be switched off, so it will reduce the energy consumption a little bit. And the 4th state is a sleep state. Here the significant parts of the transceiver are switched off, but the problem is it is not going to able to immediately receive something. We should note that recovery time and startup energy is needed to leave sleep state. That is a significant time and energy while talking about the nodes. Here is a research issue about wake-up receivers. Receiver that can be woken via radio when it's in sleep state. So here we can see the example radio transceivers. So there are several radio transceivers are available. Some of the examples, we have RFM TR1000 family. So this is the frequency range 916 or 868 megahertz, 400 kilohertz bandwidth it supports, and up to 115 2 kilobits per second. And here ASK can be used or on-off keying, and dynamically tunable output power, maximum power about 1.4 milliwatts, and it will consume less power. So these are the characteristics of RFM TR1000 family. Next example is Chipcon CC1000. Range is 300 to 1000 megahertz, and it is programmable, and it is going to use the FSK modulation, and it provides RSSI, radio signal strength indicator. And another example is a Chipcon CC2400. It implements 802.15.4, and here DSSS modem that can be used, and the frequency is 2.4 gigahertz, and it supports 250 kbps, and higher power consumption than this Chipcon CC1000. And the next example is Infineon TDA525 family. So here X represents the numbers. So here, for example, 5250, that will use 868 megahertz operated. It can be operated at 868 megahertz, and the modulation technique ASK or FSK can be used, and it will have the excellent blocking performance. So these are some of the examples of radio transceivers. We can also see some example of radio transceivers for ad hoc networks. So ad hoc network usually that will perform higher data rates are required in the ad hoc networks, and it supports up to 54 megabit per second, and it supports relatively long distance, hundreds of meters possible, typically tens of meters at higher data rates, and it works reasonably well, but we cannot say that it is perfect. Reasonably well in mobile environment, it works quite okay, but the problem here is we need expensive equipment, and it consumes more power hungry. Wakeup receivers, we know that the node will already knew that when to transmit the data, but the nodes will not know that when the reception signal will arrive. So that is the problem, energy problem, that will, the more of the energy that will be drained, keep on waiting for the reception. Idling and being ready to receive consumes considerable amount of power. So it's keep on waiting for the data to arrive. So that waiting time, that will consume some amount of power. So it is not clear that when to switch on a receiver. So we can use different protocols to solve that. So we can use contention based MAC protocols. So here the case is receiver is always on, and it is keep on waiting for the data to arrive. And another is we are going to use the time division multiple access based MAC protocols. So here the synchronization problem that will arrive, and it is inflexible. What is desirable is the receiver that can check for incoming messages, that to only check for incoming messages. Whenever the signal is detected, it wakes up the main receiver for actual reception. When the signal is detected, otherwise it is going to only check for whether is there any incoming message is arriving. If so, it will wake up the main receiver for actual reception. That is actually desirable, but it is not clear whether they can be actually built, however. So, but that is desirable. So that is whenever only the signal that is arrived, then only the main circuitry that will is going to be active and receives the data, and rest of the time the receiver part that goes to sleep state. To achieve that, we have difficulty. Optical communication, that will consume less energy. Example is passive readout via corner cube reflector. This reflection property holds only as long as the mirrors are exactly at right angles. When one of the mirrors is slightly moved, a signal can be modulated onto an incoming ray of light, effectively transmitting information back to the sender. Its main advantage is that the mechanical movement of one such mirror only takes very little energy compared to actually generating a beam of light or even a radio wave. Hence, a passive readout of sensor nodes can be done very energy efficiently over long distances as long as the reader has enough power to produce the laser beam. That means we can achieve long distance communication as long as you are having the power to produce enough power to produce the laser beam. Ultra wideband communication, we can use standard radio transceivers. Here modulate a signal onto a carrier wave. That is the technique we are going to use, and it requires relatively small amount of bandwidth. We can alternatively we can use another approach. Here we can use a large bandwidth and do not modulate, just simply emit a burst of power. It will form rectangular pulses, and these pulses are very short, and the information is encoded in the presence or absence of pulses, but it requires time synchronization of receiver, and we can achieve relatively short range in ultra wideband communication. The advantage of ultra wideband communication is it is pretty resilient to multipath propagation, and we can achieve very good ranging capabilities, and the signal that can penetrate through the wall, good wall penetration that can be achievable. And this is the reference I have used, and this is about the second session of module 4. Thank you.